Let's sketch the graph of a function. The first step in sketching a graph is finding the x and y intercepts. We'll look for the y-intercept first. The y-intercept occurs when x is equal to 0, so we can find the y value by finding f of 0. So, we'll substitute 0 for x. Simplifying, we get negative 1 plus 4, which is equal to 3. So the y-intercept is at 0, 3. Next, we'll find the x-intercepts by setting the function equal to 0. We'll isolate the constant term, then raise both sides to the 3 halves to get rid of the exponent. 4 cubed is 64, and the square root of 64 is plus or minus 8. Solving for x, we get x equals negative 9 and 7. So our x-intercepts are negative 9, 0 and 7, 0. Now we'll look at the end behavior of the graph. To do this, we'll find the limit of f as x approaches positive and negative infinity. Let's first look at the limit as x approaches positive infinity. Notice that as x gets large, the function approaches negative infinity. Now let's find the limit as x approaches negative infinity. Again, the function approaches negative infinity as x approaches negative infinity. Next, we'll check for vertical asymptotes. Vertical asymptotes occur when a function doesn't exist because there is a 0 in the denominator. In this case, the domain of the function is all real numbers, so there are no vertical asymptotes. Now we have to find where the function is increasing and decreasing. To do so, we have to find the derivative of the function. So we have f prime of x is equal to negative 2 over 3 times the quantity x plus 1 to the 1/3. Notice that there are no zeros of this function, but it is undefined at x equals negative 1. So that's our only critical point. Now we divide the domain of the function into 2 intervals using the critical point. Create a table with a row for each interval to determine if f is increasing and decreasing on the interval. Notice that on the interval from negative infinity to negative 1, f is increasing. F is decreasing on the interval from negative 1 to infinity. This means that f must have a local maximum at x equals negative 1. Now that we know that there is a local maximum at x equals 1, let's look at the behavior of the graph at x equals 1 by finding the left and right limits. We'll start with the right-hand limit of f prime. As x gets extremely close to negative 1 from the right, the function approaches negative infinity. Let's look at the left-hand limit. As x approaches negative 1 from the left, the function approaches positive infinity. We know that x is defined at negative 1, but the left and right-hand limits of the derivative are not equal, so there is a cusp at x equals negative 1. Lastly, let's look at the concavity of the graph by finding the second derivative. F double prime of x equals 2 over 9 times the quantity x plus 1 to the 4/3. Again, we find that the second derivative is undefined at x equals negative 1. Now we create a table similar to the one we used to examine the first derivative. We can use the sign of f double prime on each interval to determine whether f is concave up or concave down. Finally, we can use all of this information to draw a graph of the function.